Hi everyone, thanks for being here. Today, I'm presenting some results from our study that attempts to obtain more realistic measures of relative pollinator importance. Traditionally, pollination biologists have assumed that we can know the relative importance of a pollinator species by measuring two things. First, its interaction frequency with a plant species, and second, if you want to be very thorough, the number of pollen grains it deposits when it visits a flower, which we pollination biologists usually measure using the first virgin flower that the pollinator contacts on a plant. However, there are two additional crucial metrics that we almost always ignore. The first is pollinator movement. Given that roughly half of the angiosperm species are thought to be self-incompatible, movement patterns of pollinators among compatible plant individuals will play a significant role in determining how often cross-fertile pollen is transferred. And second, pollen carryover, which measures how quickly pollen from a previously visited individual is used up from the body of the pollinator and replaced with self-pollen as the pollinator visits a series of flowers on that same plant individual. Thus, pollen carryover provides the quantitative context in which to evaluate patterns of pollinator movement. So, given the importance of these latter two metrics in red, why haven't we studied them more often? Well, I think it's because they're very hard to study, especially in natural ecosystems that have all sorts of complicating factors. But I think that great opportunities do exist for us to study these. At least, we can take small steps in getting closer to the heart of this problem. One such opportunity is apple orchards. Apple orchards offer simplified landscapes and simplified pollinator communities, which are dominated chiefly by three bee genera here in North America: Andrena mining bees, honeybees, and bumblebee queens. This means we can collect highly replicated data on three functionally distinct pollinator taxa in apple orchards. As you can see, the flowers are also large and easy to work with, and last but not least, apple is self-incompatible at the variety level, making pollinator movement and pollen carryover important issues to study not only from the perspective of advancing fundamental pollination ecology theory, but also for the farmer's bottom line as they work to make informed trade-offs between orchard management and promotion of wild pollinator populations. So to start addressing this question, I have been working for the last 2 years with my postdoc advisor James Thomson at the University of Toronto, my undergrad research associate Sophia, and my collaborator Caroline Strang from UT Austin to document bee movement among flowers, trees, and rows of trees in orchards in the Greater Toronto region. Basically, we walk up to a tree, we look for a bee, and we follow it for as long as we can track it with our eyes. This sounds conceptually pretty simple, and it is. It just takes a lot of practice to follow these little bees as they zoom around among hundreds of other bees also zooming around. And with those data, we were able to compare the first metric of pollinator importance, which is visitation frequency. Here, I color the statistically different results in different colors using an Olympic scheme where the best pollinator is in gold, the second place is in silver, and the last place in bronze. On the right here are details of how the comparisons were statistically performed. Okay, so far so good. We can see here that bumblebees visit flowers very quickly in succession, whereas Andrena are slowpokes and honeybees are intermediate. The second metric of pollinator importance, as you'll recall, is single visit pollen deposition. We did some pollen deposition measurements, but didn't use a protocol that successfully allowed us to distinguish between outcross and self-pollen. So here I'm showing data from emasculated flowers that my good friend Mia Park has generously shared with me from her PhD at Cornell University. Thanks, Mia. You can see here that there's a dotted line. That's how much pollen is required to cause optimal pollen tube growth for good fruit set. As you can see, the vast majority of visits to the first cross-compatible flowers should result in a full pollination event in all three of our pollinator taxa. So that means that the majority of the difference among these pollinators may not be very meaningful if we consider this metric in isolation. Okay, here's the third metric I had talked about earlier, pollinator movement, specifically the likelihood of moving to a different tree after departing from a flower. As you can see, Andrena are likelier to leave the tree than the other two genera, which do not differ statistically from each other. Here's a likelihood of a special case of moving to a different tree, namely moving to a tree in a different row. This matters because in most apple orchards, a row usually consists of a single tree variety, so therefore cross-row transition events are needed to bring fresh cross-compatible pollen. Here, the Andrena and Bombus do not statistically differ, but that's largely due to the high variance we have in our data. Again, honeybees are last place, which is exactly consistent with what we see in the literature, which reports the methodical foraging behavior of honeybees on a number of different plant species. Okay, the last metric, pollen carryover. For this metric, we did some pilot studies to try building some pollen carryover curves of our own, but ultimately did not get sufficient data, especially given that COVID interfered with our field season this year. I'm sure it's a common story among all of us here. We do, however, have this excellent equation from a paper by Bill Morris and colleagues, which will allow us to build pollen carryover curves with different shapes by varying the parameters lambda and b. So here are some examples of how these parameters change the shape of the curve, where lambda determines the base of the exponential decline, which in other words means the steepness of the curve, and b determines how leptokurtic the curve is, which in other words is how fat that tail on the right side is. Now, real-world data contains lots of variance, as you can see here, some real-world data sets from that same Morris and colleagues paper. So we can modify the pollen carryover equation by adding a variance term that's centered around 1, so that we can build some wiggle into these curves to stimulate the behavior of real-world data. Here in each panel are 6 runs of the same parameters using a different variance value to show the amount of wiggle you get in these simulations. Now, with all our pieces in hand, we can then randomly draw from our real data of visitation frequencies for each pollinator species, each pollinator taxa, its pollen deposition ability, and its tree switching rate, and assign a simulated pollen carryover curve of whatever shape we choose for each series of visits by each individual pollinator. And then we can calculate the average number of full pollen loads delivered per minute for each bee taxon. Okay, so here's the result if we calculate per capita pollinator importance using the classic definition of just visitation frequency times single visit deposition. Since we don't care about pollen deposited in excess of the necessary full load of 40 grains, you can see that Bombus dominates this comparison because of how quickly they handle flowers, and Andrena comes in slightly behind honeybees, even though it has a stellar record of depositing lots and lots of pollen. As you can see, most of that pollen is in excess of the 40 grains and don't give it any advantage. But as we discussed, apple trees are self-incompatible, requiring that bees fly to a different tree in order for deposited pollen to count. So the traditional approach will give us wrong answers. When we take self-incompatibility into account by building pollen carryover curves into the simulation, we see that Andrena has now overtaken Apis, again because honeybees are much less likely to switch trees. Now recall that in most apple orchards, trees in the same row are the same variety, so we have to take this ecological context into consideration and not simply look at transition rates across trees. When we consider only row switches to start a new pollen carryover event, we see that the estimated pollination rate decreases by about half overall, and also the differences between pollinator categories become even more pronounced. But wait, there's more. We can also build in local abundance of different bee taxa to examine what each taxon is doing in terms of the proportion of pollination work that's being done at a given location. So here I give an example of the typical relative abundances in the orchards that we surveyed in the last 2 years. This is kind of what you would expect if you were to just go and do some measurements. Here's what you would conclude with respect to the relative performance of the different bee taxa if you build in local abundance but don't model in any self-incompatibility. And here are the details on the stats. Please pay attention to the y-axis because it doesn't stop at 0. And that's because I wanted to be able to show the inside of each boxes so you can see the different colors, even though maybe they're kind of self-explanatory. Here's what you get if you consider self-compatibility, but not ecological context, in our case, orchard arrangement. So you can see that Andrena and Bombus are both gaining in on the honeybee. And here's what you get if you also consider orchard arrangement. So at this point, Andrena has fully overtaken the honeybee, and Bombus is getting close, despite being so much less abundant. Okay, lastly, the shape of the pollen carryover curve is important too. As a concrete example, here's that comparison I showed you just now, using a carryover curve of lambda equals 0.6. And here, you see a rank reversal between Andrena and honeybees when we run the same simulation, but using a shallower carryover curve of lambda equals 0.05. And there are strong reasons to expect that pollen carryover curves should differ across plant species with different floral morphologies and inflorescence arrangements, as well as across pollinator taxa. For example, Andrena carries pollen loosely held in its fluffy scopa, where older layers of outcross pollen from previous trees or rows may get mixed to the surface and get deposited onto stigmas even after visiting many flowers, while honeybees wet their pollen and meticulously groom the grains into their corbiculae, where the pollen is likely permanently removed from circulation very quickly. So I think constructing different pollen carryover curves for different pollinator taxa is probably one of the next big hurdles that we pollination biologists need to tackle. So in conclusion, we can get much more realistic estimates of the relative importance of pollinators even just by following them around and quantifying their tendency to switch from one plant individual to another, and applying some informed guesses about what pollen carryover patterns look like. I think this is something that we should try to apply much more often in our pollination studies, not only in commercial orchards where trees are nicely arranged in same variety rows, but also in the majority of pollination systems in nature too, because at the very least, most plant species tend to simultaneously display multiple flowers, even for small annual forbs, like the two that I'm showing on the right-hand side. Okay, so with that, I would like to thank the people who made this work possible, and NSERC for funding my postdoctoral fellowship and research expenditures. I particularly want to thank my collaborating apple growers who have generously allowed me to work on their property and have kindly accommodated all of my methodological requests as I figured out various parts of my study. And of course, thank you once more for listening, and at this time I'm happy to take your questions.